Welcome to lecture 9 of linear algebra, also the last lecture of linear algebra. In this lecture, we're going to talk about the Jordan form. So, the Jordan form is motivated by the desire to simplify the study of matrices, particularly in the context of diagonalization. And since we have seen in previous lectures that diagonalization um, is not always possible for all the matrices, so the Jordan form provides an alternative canonical representation for matrices, including those that cannot be diagonalized. And throughout, we shall work with a finite dimensional vector space. Of course, we want it to be a complex vector space, namely V. Even though some of the some of the concepts make sense for real vector spaces as well. Essentially, whenever we have a real operator which has as many real eigenvalues as possible, meaning that it has dimension of the number of real eigenvalues with the counted multiplicities. Okay, so first let us define the Jordan block. So a Jordan block of size k is a k by k matrix of the form, namely jk of, for example, lambda 1 is the matrix lambda 1, 1, lambda 1, 1, and we have 1, lambda 1, and being all the missing entries are being 0. So that is a Jordan block is almost a multiple of the identity, except that we have the ones are above the lambda 1, above the even diagonal. And know that the characteristic equation of lambda 1 minus lambda to the kth power it is the characteristic equation. And so the only eigenvalue is lambda 1. And the eigenspace corresponding to this eigenvalue is one-dimensional, and it is spanned by an eigenvector of 1, 0, 0 with its transposed. So the Jordan form, we say a square matrix is said to be in Jordan form if it is block diagonal where each block is say Jordan block. Okay, so now if our V is a non-zero generalized eigenvector of T, of a linear operator T, which is corresponding to the eigenvalue of lambda, then there exists a smallest positive integer k such that our T minus lambda I kv vanishes. So the consequence is that v T minus lambda I v all the way down to T minus lambda I to the k minus 1 v, and this side is a linearly independent side. And observe that for a matrix maps the vectors of the standard basis given by our AE1 equals to lambda 1 E1 and AE2 equals to lambda 2 E2 and of course AE3 equals to lambda, okay, sorry, so AE1 is lambda 1 E1 and AE2 is lambda 2 sorry, it's lambda 1 E2 plus E1, and AE3 equals to lambda 1 E3 plus E2, and so on. So our E1 is an eigenvector, and the rest of EJ are called the generalized eigenvectors. We can generalize this into the definition. So A is a square matrix. And lambda is an eigenvalue, and V is non-zero eigenvector, such that we have AV equals to lambda V. So the first generalized eigenvector attached to V is the solution V1 of the equation. AV1 equals to lambda V1 plus V. And the second is that AV2 equals to lambda V2 plus V1, and so on, so on, so on. So we have AJ, AVJ plus 1 equals to lambda VJ plus 1 plus VJ for so the generalized eigenvectors lambda 1, V1, V2. So suppose it terminates at k, which is smaller or equals to n, and this sometimes is called a chain, a Jordan basis or a Jordan chain. So there is a theorem. Yes, theorem 1. This is Jordan's theorem, and it states that for any linear operator, namely L, okay, let's use T on V, there exists a basis consisting of eigenvectors and generalized eigenvectors. Okay, so the existence is for certain. And this basis is the Jordan basis. Is sometimes is called the Jordan chain for the linear operator T. And recall that for two matrices A and B, they are similar if and only if there exists a non-singular C matrix C such that A equals to C, B, C inverse. Also, this relation is an equivalence relation, and geometrically, this means that they represent the same linear operator and encode it with respect to two different bases. So the matrix of the operator with respect to its Jordan basis has a Jordan form, which consists of diagonal blocks, and each block being the Jordan block. So a corollary is that every square matrix is similar to its Jordan form, and so of course two matrices are equivalent or are similar if and only if they have the same Jordan form, and of course up to some permutation. So permutation of Jordan blocks. Okay, so if A is a matrix and J is its Jordan form, then A equals to B, J, B inverse, where B is the matrix columns being eigenvectors and generalized eigenvectors. And if we let lambda be a specific eigenvalue for the operator T, then we know that there is a basis for the generalized eigenspace of T corresponding to lambda consisting of the Jordan basis. A natural question to ask is that how many Jordan bases are there? The final vectors in these Jordan bases are, of course, the eigenvectors corresponding to the lambda, which in fact give a basis for the eigenspace corresponding to lambda. So that is the number of the Jordan blocks in the Jordan form of T corresponding to the lambda, or the number of Jordan bases corresponding to lambda in Jordan basis of the underlying vector space V. It's just the dimension. So yes, this is a lambda. It's the dimension of the usual eigenspace of T corresponding to lambda. And the problem we are now interested is in how to find the Jordan form of a given linear operator. And the characteristic equation tells us how many times a certain eigenvalue will appear in this Jordan form by the multiplicity. And the dimension of each eigenspace tells us how many Jordan blocks there will be for specific eigenvalues. And what about the size of the blocks themselves? And the important fact is given by this result, that is the size of the largest Jordan block corresponding to an eigenvalue lambda of T is exactly the degree of the example G minus lambda term in the minimal polynomial of T. Okay, so many results of the many exercises of the Jordan block could be found in the we will not include them there. So yes, these summarize all the everything we do in linear algebra. So too many details, and I think those details could be could be found in better treated notes or some online lectures. Okay, so now I want to close our lecture. This is only there are only 9 lectures and doing very well for our description in linear algebra. Oh, one more thing is that z minus lambda here for our z is only the, for example, corresponding to the characteristic equation in the first entry. Okay, so thank you for watching, and
and see you in other lectures.